Astronomers may have discovered that the closest black holes to Earth could be lurking in the Hyades cluster, which sits only around 150 light-years from the Sun. In fact, these black holes may have been ejected from the dense cluster of stars millions of years ago to wander the galaxy alone. Even so, they would still be around 10 times as close as the black hole previously considered the closest to Earth. Visible in the constellation of Taurus, the Hyades is an open cluster of hundreds of stars. Open clusters like this one are collections of stars believed to have formed at the same time from the same massive cloud of gas and dust. Because of that, stars within this kind of cluster are known to share foundational characteristics like chemical compositions and ages. Astronomers have made a groundbreaking discovery: a highly unusual black hole named Gaia BH1, located about 1,500 light-years away from Earth. This stellar mass black hole, 10 times the mass of the Sun, is part of a binary system with a Sun-like companion star. However, this seemingly ordinary discovery has left scientists puzzled and challenged long-standing models of binary system evolution. The peculiarities of this system have revealed significant gaps in our understanding of the universe. The mysterious binary system. Binary systems consist of two massive celestial objects, such as stars, planets, or black holes, bound together by gravity. In Gaia BH1, a G-type main sequence star, similar to our Sun, orbits the black hole in a highly elliptical orbit with a period of 185.6 days. The orbit's eccentricity, 0.45, and the wide separation between the two objects are phenomena that defy existing astrophysical theories. In order to make the detection of what could be the closest black holes to our planet, a team led by Stefano Torniamenti, a postdoctoral researcher at the University of Padua, created a simulation of the movements and evolutions of stars in the Hyades. The simulation was also generated with black holes present in the equation. The scientists then compared results from this simulation with actual observations previously made of the velocities and positions of the open cluster's stellar population. The latter dataset owes itself to the Gaia Space Telescope. This is because, the team says, if those black holes had been violently tossed from the Hyades when the cluster was around a quarter of its current age, approximately 625 million years old, the collection of stars would not have evolved enough to remove evidence of their prior existence. Even if the black holes have been ejected from the Hyades by now, the researchers explain, they would still remain the closest black holes to Earth despite their rogue status. That is according to the simulations, which indicate that if the black holes aren't currently in the Hyades, they are still close to it. Prior holders of the closest black hole to Earth record were Gaia BH1 and Gaia BH2, which, as their names imply, were uncovered with Gaia data just this year. Gaia BH1 is located 1,560 light-years away from Earth, while Gaia BH2 lies around 3,800 light-years away. Even though this means both black holes are located in Earth's backyard, in cosmic terms at least, they are still over 10 and 20 times as far away as the Hyades cluster and its potential black hole duo or trio. Both this new research and the prior discovery of Gaia BH1 and BH2 exemplify how Gaia, launched in 2013, has been reshaping astronomy. The Space Telescope made it possible for astronomers to study the positions and velocities of individual stars in clusters like the Hyades for the first time. Gaia is capable of such breakthroughs because it can accurately measure the positions and motions of billions of stars against a background sky. Tracking stellar movements with such high precision helps to reveal gravitational influences tugging on these stars, even if that influence comes from hidden objects like small stellar mass black holes. This observation helps us understand how the presence of black holes affects the evolution of star clusters. Researcher, author, and University of Barcelona researcher Marc Gilas said, "These results also give us insight into how these mysterious objects are distributed across the galaxy. Typically, black holes of Gaia BH1 size are found in close orbits with their companion stars, often drawing mass from them. However, this system shows no evidence of mass transfer between the star and the black hole. The two objects are gravitationally bound, but maintain a relationship that does not fit any current models, leaving scientists to question how this arrangement could have formed without destroying the star." The challenge to known models. The discovery of Gaia BH1 challenges the common envelope model, which is a leading theory for explaining the formation of close binary systems. In this model, a massive star expands into a red giant and engulfs its companion star within its outer layers. The resulting friction and dynamic interactions cause the system to lose energy, narrowing the orbit of the two objects and ejecting the envelope. However, Gaia BH1's wide orbit makes this scenario implausible. Additionally, the Sun-like star in this system lacks the mass necessary to strip the outer layers of the progenitor star that eventually collapsed into the black hole. Another hypothesis, the triple star model, suggests that the system originated from a triple star configuration. This would involve two massive stars in a close orbit and a third lighter star, the G-type star, orbiting farther out. The inner stars could have evolved into black holes or merged, leaving behind the current system. However, this model also falls short of providing a complete explanation, as such triple systems are often unstable and difficult to reconstruct with certainty. A dormant black hole. Unlike active black holes that draw matter from their companion stars and emit strong X-ray radiation, Gaia BH1 is a dormant black hole. It reveals itself only through its gravitational influence on the companion star. The data from the European Space Agency's Gaia mission, which has been mapping over 1 billion stars in the Milky Way since 2013, was crucial in identifying the black hole. Subtle wobbles in the star's motion confirm the presence of a black hole, as these oscillations are unique to such massive objects. A rapidly feeding black hole at the center of a dwarf galaxy in the early universe, shown in this artist's concept, may hold important clues to the evolution of supermassive black holes in general. Using data from NASA's James Webb Space Telescope and Chandra X-ray Observatory, a team of astronomers discovered this low-mass supermassive black hole just 1.5 billion years after the Big Bang. The black hole is pulling in matter at a phenomenal rate, over 40 times the theoretical limit. While short-lived, this black hole's feast could help astronomers explain how supermassive black holes grew so quickly in the early universe. Supermassive black holes exist at the center of most galaxies, and modern telescopes continue to observe them at surprisingly early times in the universe's evolution. It's difficult to understand how these black holes were able to grow so big so rapidly. But with the discovery of a low-mass supermassive black hole feasting on material at an extreme rate, so soon after the birth of the universe, astronomers now have valuable new insights into the mechanisms of rapidly growing black holes in the early universe. The black hole, called LID-568, was hidden among thousands of objects in the Chandra X-ray Observatory's Cosmos Legacy Survey, a catalog resulting from some 4.6 million seconds of Chandra observations. This population of galaxies is very bright in the X-ray light, but invisible in optical and previous near-infrared observations. By following up with Webb, astronomers could use the observatory's unique infrared sensitivity to detect these faint counterpart emissions, which led to the discovery of the black hole. The speed and size of these outflows led the team to infer that a substantial fraction of the mass growth of LID-568 may have occurred in a single episode of rapid accretion. LID-568 appears to be feeding on matter at a rate 40 times its Eddington limit. This limit relates to the maximum amount of light that material surrounding a black hole can emit, as well as how fast it can absorb matter, such that its inward gravitational force and outward pressure generated from the heat of the compressed, infalling matter remain in balance. These results provide new insights into the formation of supermassive black holes from smaller black hole seeds, which current theories suggest arise either from the death of the universe's first stars, light seeds, or the direct collapse of gas clouds, heavy seeds. Until now, these theories lacked observational confirmation. The new discovery suggests that a significant portion of mass growth can occur during a single episode of rapid feeding, regardless of whether the black hole originated from a light or heavy seed, said International Gemini Observatory NSF Noir Lab astronomer Hyewon Sui, who led the research team. A paper describing these results, a super Eddington accreting black hole approximately 1.5 gigayears after the Big Bang observed with JWST, appears in the journal Nature Astronomy. Implications for Astrophysics. The Gaia BH1 discovery highlights the limitations of current astrophysical models and the need for new theories to explain phenomena in the universe. The system's isolated location, unusual orbital dynamics, and lack of mass transfer between the star and the black hole suggest that our understanding of binary system evolution is incomplete. Gaia BH1 serves as a reminder that the universe holds many secrets yet to be uncovered. It underscores the importance of missions like Gaia, the James Webb Space Telescope, and other observatories which continue to push the boundaries of our knowledge. The road ahead. As scientists delve deeper into the mysteries of Gaia BH1, they hope to uncover the forces that keep this extraordinary system in balance. Could there be undiscovered physical phenomena at play, or does this system hint at entirely new principles of astrophysics? While the answers remain elusive, one thing is certain. Discoveries like Gaia BH1 propel humanity closer to understanding the universe's most profound mysteries. Stay tuned for more updates as astronomers unravel the enigma of Gaia BH1 and redefine our understanding of the cosmos.